Let me start with a quick reminder that Lab 1 is due tonight. So the way the labs work is there's actually 3 things you need to do to get credit for a lab, and you do need to do them all for all the labs in order to pass the course. So the first thing you need to do is to check in your design. So each lab comes with a checkoff file, and that basically has a little test jig in it that runs your circuit through its paces and then checks to see whether you're getting the answer that we expect. When you press the little green check mark, it takes the simulation that you've run and checks it to see that it's right, and then if it's in fact right, you can then submit it to the online system. So you got a little box where you can type in your Athena name and your password, and it uploads it to our system. So that's step 1. Step 2 is that you need to arrange for a checkoff interview. Please just come to any of the staff lab hours. Any of the LAs or the TAs can have the checkoff interview. It's a short discussion about that week's design. You can do that sort of any time, but you have to have it complete for full credit. You need to have it complete by a week after the check-in of your design is due. So the checkoff interview for full credit for Lab 1 would have to be complete by next Thursday. Please don't wait until Thursday evening after it's due in order to do your checkoff, because things get busy. My recommendation is there's some staff hours on Friday or early next week. That would be a great time to do your checkoff interview if you haven't done it already. The other thing you need to do is that with most of the labs, there's some online questions that you need to complete. And so those are just something that's related to the design task of the week. And you can find those on the online assignments page. So those are the 3 things you need to do to actually see the points for the lab appear on your online status page. Any questions about what's due for labs, or when, or how, or who? Yes, sir. When are the lab questions due? There's actually not a deadline associated with the lab questions. Most people get nervous when they don't see their lab points appear, and so then there's a small motivation to earn the points. You do need to complete the questions, but there is no official deadline for the lab questions. Any other? Yes?
The lab Q link on the website?
Yes, the lab Q link. So when you're in the lab and you would like to get some help, if you click on the Lab Q link, you're able to put yourself on sort of an automated queue system, and then the staff who are in the lab look at that to see who to help next. So standing around with your arm up gets very tiring when the lab gets full, so we basically have an automated system for saying, put me in line, and then we sort of try to help people in the order in which they added themselves to the online queue. If everybody here should be registered to be able to get onto the online queue. If you're not, just send me a quick note, and then I can see what the problem is. Any other questions? Okay, and then along in the announcements mode, we're having a quiz a week from Friday. That quiz will happen in your section, so the section you've been going to Wednesdays and Fridays. And if you haven't been going to a section, there's one that you should be going to or could be going to. That's where you should show up to take the quiz. It's a closed book quiz. It's 50 minutes. It'll be short answer. We will be posting some quiz review videos early next week. Well, we have plenty of old quiz problems and tutorial problems for you to try, complete with answers. And then there's Piazza if you want to ask some questions. And finally, staff in the lab. There's no lab due next week, so the lab hours would happily be used answering any questions you have about how to do a particular type of problem. So there's lots of opportunity for you to test your skills ahead of time, but then we'll actually test them for real Friday during section. We hand back the quiz the following Wednesday, and away we go. Any questions about the quiz? There's information on the course website about what it covers and things like that. Okay. Well, in 6004 so far, what we've done is we started off in the sort of real but messy world of analog electronics, where electrons flow and time runs continuously, and voltages can be any value. And we tamed that beast by imposing a digital discipline where we came up with a representation for bits, for zeros and ones, and used that voltage representation. And we used that along with some voltage-controlled switches to design machinery that is able to signal digitally and to process digital signals using Boolean logic in order to perform interesting functions. And the rest of this course is really thinking about interesting functions we can build with logic, and in particular we'll be spending a lot of time building ourselves a computer. Or you'll be spending time building a computer, and we'll be talking about how to do that. And so the first step in that stage was to design combinational logic, and we came up with the static discipline and truth tables and various implementation strategies to actually build logic gates. And it's interesting to ask oneself, is that all we need? Can we actually build a computer with what we know so far? And the answer is no, we're missing one thing. So what's the thing we can't yet do? And so here's a little word description, but it's easier to watch the animation. So when our assistant here presses the button, the light goes on. And if he presses the button again, the light goes off. And on and off. And what's interesting about that is that the light, the state of the light, which is the output of this particular device, is clearly independent of the state of the button. In other words, it's not on when the button is pressed and off when the button is not pressed. That you could implement in combinational logic. The behavior that's shown here, which depends on the history of the button presses, in other words, the light basically changes its state from on to off every time the button is pressed. This notion of history, where the function of the output, in this case the state of the light, is not simply a function of the state of the input, which is the button. It has to do with what's happened in the past. So we're going to have to change or add something to our toolbox that lets us talk about the notion of state. And state is sort of a summary of previous history, sort of encapsulated, we've extracted from that history the information we need and remembered it. So the notion of a state is sort of our way of capturing the notion of a memory. And so we have a notion of state. And the other thing that we sort of notice is that there's this notion of pushing the button. So we're talking sort of about button pushes. Notion of events as opposed to just, is the button pushed or not. There's sort of like the same thing, the difference between a mouse click and sort of just where we're sort of trying to identify an instant in time. And you'll see that show up in today's lecture too. So we're going to add to we love to use clouds here as a representation of combinational logic. And combinational logic, of course, has some number of inputs. And we know that if the inputs to the combinational logic cloud, our logic circuit, have been stable for at least TPD, we can expect to find digital stable values on the outputs, and they will not change any further until we change the inputs again. We're going to add to this basic recipe, this basic idea of how to manipulate digital information, a new device called a memory device. And the notion is that it represents the current state, encoded in some number of bits. Now, this sort of very high-level, notional diagram of a digital circuit is actually complete now, with a notion of state and a state-holding device combined with combinational logic. That, if you will, is the schematic diagram of every digital system we can build. Your laptops have a lot of state in them, millions of bits of state. But conceptually, they have something that holds the state and something that manipulates the state, the current state, combines it with the inputs, produces new outputs, and a notion of a new state. And then at a certain instant of time, we can choose to move to a new state. And then the whole process repeats again and again. We're going through a sequence of states. So this type of logic, the combination of memory devices and combinational logic, is called sequential logic. So called sequential because we're going to go through a sequence of states. And the notion is, when do we actually change the state of the device? Well, it depends on what we're trying to do. You have a clock. It's a periodic signal that goes high every billionth of a second, or half a billionth of a second, depending. I have a 1 gigahertz or a 2 gigahertz processor. And so your computer is busy updating its state with a new state, a billion times a second. And that's what makes the world go around, at least in terms of digital processing. So we've introduced some new notions here. We have a notion of sort of a current state, which represents our notion of history up to now. We're going to combine that with the inputs to compute a next state, and then at a certain instance of time, we'll transition to the next state and repeat that recipe again and again and again. So we're going to spend a little bit of time now thinking about how to actually build this storage device. Yes?
Doesn't it cause issues because in general we're not allowed to have cycles?
We're not allowed to have cycles.
That looks suspiciously like
This looks suspiciously like a cycle, and in fact, this will be the only cycle we allow ourselves. In some ways, the only place that we're going to allow ourselves to sort of make this loop is right at the storage elements. And you'll discover in a moment that we actually, the actual circuitry that we're going to use to build a memory device is itself not a combinational circuit. It will be a circuit that itself has a positive feedback loop in it. That's how the storage will be implemented stably. So it's a good observation that in fact we're breaking our notion of allowing ourselves a cycle, but they're going to be engineered cycle. You can't willy-nilly make a cycle. You can only make a cycle in a sense at the input and output of a storage device. Okay, so cycles that don't include one of these storage devices will continue to be disallowed. We won't allow combinational cycles. Okay, so to build, we already know some things that do storage. We build ourselves some read-only memories, things that would allow us to sort of do a table lookup on the value of a function. Those are indeed a type of memory. They're logic circuits that sort of produce, you give them the same inputs, they produce the same outputs, and there's some memory in there somewhere. But we're going to be interested today in state that we can actually change, that isn't constant over time. And so we're going to have to think about, what's the machinery we can do? And there's lots of mechanical representations, punch cards or, things like that, paper tapes, and those were the types of state that people used back in the 50s and 60s to sort of remember things from moment to moment. More recently, everybody has probably CDs or DVDs at home, and they represent all the digital information about the music or your picture in terms of these little reflective bumps in a mirrored coating, and then we shine a laser on it, and we can sort of detect the presence of the bump or not as the CD spins under the laser head. That's another way of representing information. The writing of CDs and stuff, that's actually a complicated device. Getting rid of old bumps and putting in new bumps is actually a slow process by, at least in terms of the sort of billionths of a second that we're using here in our laptops. So magnetic materials, changing the sort of north or south orientation of these little magnetic particles or magnetized particles on a piece of mag tape. We could do that. We could send information way out and have it come back, so we could say, I want to remember this for a whole day and design a transmission system that takes a day, and sure enough, a day later, we'd be getting the information back, and we'd going, thank you for reminding it. That's not a very convenient storage mechanism, but it's certainly another way of doing memory, is arranging that at some later point in time, the information will reappear. And if we could use it then, or we can send it on the same loop again and again and again. We're actually going to use things that represent some sort of electrical system, circuitry that can remember things. For instance, storing a voltage on a capacitor, which would let us, quickly and access things right away, and also quickly change them. Here's a little very simple schematic diagram that's actually pretty representative of the dynamic memories that you have in your laptop. We'll be talking more about this in the future, but today, just think of this as a voltage-controlled switch and a capacitor. So when we want to put information onto the capacitor, we close the bit switch so the changing plate, the sort of read-write plate of the capacitor is connected to the bit line, and then we we drive the bit line with a big inverter with either 0 or 1, and that will charge or discharge the capacitor as appropriate, and then we open the switch, and now the capacitor is just sort of sitting there going, okay, you put some charge on my plate, I'm going to remember that. And unfortunately, there are some things, that electrical phenomenon that will cause the charge here, cosmic rays and things like that can cause the charge to actually be blown off the plate. There's a certain amount of leakage current, both through the MOSFET and perhaps through the dielectric of the capacitor, which will cause some of that charge to leak away. So this sort of storage scheme has the problem is that you might have to come back and refresh it. And in fact, every 10 to 20 milliseconds, all the information is read out of your dynamic memory and then rewritten. So the thing I like to think of is, did you ever, when I was young, there was these circus acts where there'd be this guy with poles, and he would start spinning plates on the poles, and he would do that, and with 3 or 4 or 5 or 10 plates. And then sort of by the time he got to the last one, the one at the end would start to wobble, and he'd have to run all the way back to the other end and make it spin fast again, and it was using the sort of momentum of the plate in order to keep it stable on the pole. And as that momentum died away, the plate would start to wobble. And if he didn't want the plate to fall off, he'd have to come back and refresh it. He'd have to give it more momentum again. Well, that's exactly what has to happen to this bit. We have to come back and read it out before it's disappeared. Too much charge has leaked away. And then rewrite it. The readout process is sort of tricky because we have this bit line. If there's a lot of these cells connected to it, it has a high capacitance. We have a little capacitor here. We don't want it to be too big because we want 1 billion of them on a chip, or many billions now. And so, in fact, it's a very tricky analog piece of circuitry where we connect this little capacitor to this big capacitance of the bit line and look for a very tiny, on the order of several millivolts change in the voltage and say, aha, a 1 or aha, a 0, depending on which direction the change is in, and sort of go from there. So this actually works, but has a lot of subtle electrical problems that is not terribly convenient for us. Suppose we have come up with a circuit where we just stand there and spin the plate continuously. In other words, it never wobbles. We don't let it ever to get into a state where we have to rush back and start it up again. And we can build such circuits. Now here's our engineered cycle, the one that we're going to allow ourselves in the circuit. Okay, we're going to use this positive feedback loop. So if we start off and we design ourselves just 2 inverters in a row and talk about V in and V out, if we did the V in, V out diagram of such a device, so this is V out on this axis and V in, and we ran a bunch of experiments, we would discover the V in versus V out curve looked like this. A low on the input will produce a low on the output, and a high on the input will produce a high on the output. And so that's sort of tells us the behavior of this circuit sort of statically. For a given V in, we'll have a given V out, and it looks like that. Now suppose we come in and we now make a connection between the input and the output, like so. So we're going to add a new constraint to the device, which is this line. Now the V in equals V out line, and we discover that the circuit that has to now obey both constraints, the VTC of this part of the circuit, and then the constraint imposed by connecting to the input to the output, I put those 2 graphs together, and I can identify 3 separate solutions that the physical world could find. It could find one where V in is low. This voltage is low. This one will be high. That one will be low, and that's all consistent. This could be high, right? So either high or low on V in is a perfectly good solution. One that's stable. Stable in the sense that so long we don't unplug our circuit, we can expect to, start this guy at 0, and this guy will be 1, and this guy will be at 0, and as long as we keep it plugged in, a little bit of noise here won't matter because this logic gate is a restoring logic gate. It's a combinational device, right? So little bits of noise here won't really change what comes on the output here. So noise does not affect this circuit, and in fact, it will maintain this bistable loop. Bistable because there's 2 stable voltages. This middle point is actually very sensitive to noise. It is a solution to the system, and one that will cause us some angst, but we're going to save that angst for a week from today. So stay tuned. We'll come back to that point and spend a whole lecture going, what do we do about this? And the answer turns out to be somewhat involved and well, we'll save the chapter 17 will be the middle point. Meanwhile, let's work with the two stable points. So what we're going to do is we're going to take a multiplexer. So this circuit is fine. The trouble is that it's stable, but we don't have a way of introducing a new value into the loop. So instead we're going to use a multiplexer. And let me just remind you what our multiplexer looks like. Our circuit for our multiplexer looks like, right? So there's these two AND gates. I'm going to do it all with NAND logic. So I'm going to write a demorganized NOR gate, which is another NAND gate, like so. I'm going to make this guy loop around. This will be the D input here. And then I have this so-called gate signal coming into this gate. And I'm going to come up here and put them through an inverter to that gate. So that's what that multiplexer circuit looks like. You can see that when G is 1, the behavior, so we're going to make this loop. When G is 1, the behavior is, that means this gate is on and this, if this is a 1 coming in here, so if we put a 1 here, that means this guy is a 0. So this gate is always, is basically always turned off. The AND gate isn't participating here. With a 1 here, whatever comes in on D will show up on Q. So when the gate is open, the G signal is high, information flows through this device. The interesting part comes when G is low, so that's shown here on the first couple lines of the truth table. Because of the feedback loop, what we have here, think of it now as this is a NAND gate and another NAND gate organized in such a way that we actually have this positive feedback loop going on. Those two inverters in a row. The VTC of this configuration when G is 0, or when G is 1, but, when, I'll say it right, when this G is 0 and this guy is 1, the VTC of now this path here is the one I showed on the previous slide. It's the one that will be bistable. So we have this sort of programmable positive feedback loop where when the gate is open we can put in a new value, and when the gate is closed that value will be remembered by this circuit as long as we continue to supply power. And in fact it's stable against noise. Any little noise that happens on the nodes in the circuit will be cleaned up as it passes through the next gate in the loop. Okay, so this is going to be our engineered cycle. So we have a new device called a latch. And so you can just sort of see the behavior here. So when, the behavior is that when G is high, if I change D up here, propagation delay later, that shows up on Q. And if I change D up here from V1 to V2, then after a propagation delay, that output, the propagation delay of the latch, the Q output will reflect that. And now G goes low, and so G is another input. We're a little worried about if I change G here, do I have to worry about the Q output? So if I change G, in sort of the most general case, we'd expect Q to sort of go bonkers. In other words, it's allowed to do anything it wants, okay, until the propagation delay, in which case it has to come up with a final stable digital value. But notice we're relying on this guy to sort of try to remember, and it would be bad for our memory to suddenly go, oh, right as we say, okay, I want you to start remembering, and it goes, oh, I've forgotten. I'm in a positive feedback loop, but meanwhile, in the transition to getting into the positive feedback loop, I've forgotten everything. So we have to think a little bit about that, and we're going to dip back into our bag of tricks and think about using a lenient multiplexer, one that so long that the D and the Q inputs here are enough to determine the output value, G can change without corrupting the output. We're going to try to put ourselves in a situation where we don't have this contamination problem where we suddenly forget everything. So we're going to use a lenient mux. And a lenient mux has the behavior, well, there's sort of a couple modes here. Here's a schematic diagram for a lenient latch. So we're in a mode here where if G is 1 and D is stable for long enough, so the two inputs are now have both been stable now for TPD, we can expect Q to be valid and be stable after a TPD. So a TPD after D changes, assuming G is not changing, we're all set. Okay, so that's good. We can be in a situation now where if D and Q are both stable, so look on the graph here and find times when D and Q both have the same value. At this point, we're sort of saying, look, it doesn't really matter whether you're selecting the top input or the bottom input on this multiplexer with the feedback path, because they're both the same value. So D and Q prime here have the same value. Okay, and now G can change without corrupting anything. So that's what it would mean. That would be true if this was a lenient implementation of a latch. And in fact, we showed you the schematic diagram of that in a previous lecture. Now we're in a situation that we can, once G is safely low, once G is low and Q has remained stable, now the D input can change without any problem. And now we're in memory mode. Once we've gone in here, the information is now held in the internal feedback loop, and Q will remain stable as long as G is low. Everybody sort of happy? Are there questions about this sort of transition from loading it up to going into this positive feedback loop mode, and that by using a lenient multiplexer here in our latch circuit, we've avoided the problem of it suddenly, forgetting everything? We're relying on this sort of middle region here. When both D and Q prime, or Q, are stable, we can change G without the output changing. That's what it would mean for the latch to be lenient, that mux to be lenient. It's sort of a key thing, right? We've had to do some careful engineering to make this happen, but having done the careful engineering, we can safely let the cycle in our circuit do its job, which is to be our memory. Okay, so does this guarantee a working latch? Have we taken care of all the problems? Have we dealt with all the possible situations of D changing and G changing? And the answer is almost. Okay, we're going to have to introduce a new set of rules that takes care of one more situation. And that's the situation, what would happen if D and G, the data input and the gate input, changed at the same time? In particular, we're worrying about when G goes from high to low. We're worried about, so we're in a situation here. So here's the G signal going from high to low. So here we're in, the gate is open, and here's the gate is closed. What would happen if D decided to change about the same time? In other words, we're not quite sure what we're asking the device to remember. Are we asking the device to remember this value or that value? There's some places in here where if D changes, maybe just a little before, it's not clear whether we want the device what we want the device to remember. And our timing analysis on the previous page sort of suggests that we don't want D to be changing, okay, while G changes. So we're going to have to introduce another set of rules for this particular latch device, okay, that is another discipline that we're going to have to follow, something we call the dynamic discipline. So here's how those rules work. When the G is open, at some point, we're going to change the value of D, okay, and that's okay. We're allowed to wiggle D all we want when the gate is open on the latch. We're setting up this new value. And after TPD, we know that the change in D has been reflected in the value of the Q signal. In other words, that information is propagated through the latch. Okay. If we wait for another TPD, okay, we know, so that means that the Q signal has now become stable right after the end of the first TPD, because that's when Q became stable. So the Q prime input, which is just Q, has now become stable. If we wait for another TPD, now the value of Q on the output reflects the fact that both Q prime and D have the same value. And now it's safe to change G. So if we have this discipline that D has to wait, has to be stable for 2 times TPD before G can change, we're in a situation where our lenient mux is guaranteed to work correctly. And so we're going to give a special name to this delay between the last change of D, of the D input, and when the G is allowed to change. and that's called the setup time. In other words, the input, the D input, has to be stable for a certain amount of time before we switch from the latch being open to the latch being closed. Yes, sir?
Why do we need two TPD? Because by after one, we know that Q is stable.
We know that Q is stable and it reflects the current D input. What we don't know is whether the information that Q prime is also stable has propagated all the way through the internal circuitry. And with our very simple timing model, we have to wait for another TPD for every node, everything that's inside of the circuit to know that these are both now at the same value, D and Q prime. Once that's true, then we can use the lenience property of the mux to actually change the G signal without worrying about corrupting the output. Does that make sense? So that's why we have to wait that second TPD. Now, in fact, in many electrical circuits, you can actually wait a little less than that. And you'll discover that if you actually pick up a data sheet for a latch and read about the various timing constraints, that the setup time is often less than twice the propagation delay. But for our very simple timing analysis, this is sort of all the best we can do given the knowledge we have. The only thing we know about the timing is the TPD timing. Okay. Similarly, we have to wait, once G goes low, we have to wait for the G going low information to propagate all the way through the circuit before D would be allowed to change again. So we come up with this notion of a stability. We're going to have a window of stability around the falling edge. So D can do anything it wants, and then at some point it has to become stable, and at some point G can change, and then later on D can start changing again here. We have this region of stability, and the time before the falling edge of the gate signal is called the setup time, and the time of stability after the falling edge of the signal is called the hold time. Okay, so setup and hold. So in addition to TPD, for these memory circuits, we have two other specifications. Okay, setup time and hold time. And we'll discover that, as we'll see when we start using these circuits, in larger circuits, using latches and in larger circuits, that will be very important for us when we're doing the engineering of those circuits. We'll have to make sure that the input to these latches aren't changing, too close to when we're going into memory mode, in order for the memory to be reliably set without any possibility of corrupting the value we're trying to remember. Yes?
But then by the simplicity, why does T hold only have to be TPD and not another T?
Because once G is 0, once that's propagated through the circuit, now the Q output reflects the fact that G is 0, which means our positive feedback loop is in place stably, reliably. We don't have to wait again. So before we had both the D to output and then Q prime to output. That's what was the two-pass thing. Here we only have a single pass of G through the circuit, and now we're all set. Now we're in positive feedback mode. Okay, so this is called the dynamic discipline. So in addition to the static discipline, we also have the dynamic discipline. And those two rules about the timing of your circuit is what controls the engineering. That's, as we'll see, that's what makes the your processor, a gigahertz processor instead of a 2 gigahertz processor. We had to leave enough time for these timing constraints to be true. Let's try it out. Okay, we're going to put this neat little latch in here. We're going to say, okay, let's use this new device, our new memory device. And when we want it to change from the current state to the next state that we've carefully computed here, I know, let's just put a 1, open up the gate, and let that new value through. But now we have a small problem. If we leave the gate open too long, what will happen? Well, the new state will become the output, the so-called current state. It'll zip through the cycle, and we basically build ourselves a big loop here. A big cycle. And so this thing will sort of wildly spin away, again and again. So we've got to start on a memory device. The trouble is, in the exact configuration that we wanted to use it, we have this sort of notion of, I want to open up the gate long enough to let something through, but not long enough for it to propagate through the circuit and come back to my input again. So we go, whoop. Was that quick enough? I don't know. So as the little guy here says, this is we're sort of on the right track, but this sort of tricky business of opening the latch for just long enough to let a new value through, but not long enough for that new value to affect our input because of the cycle. So we're going to say, well, not quite there yet, Chris. Okay. Alrighty, so to demonstrate our problem, you've just come in from Logan. Your friends have picked you up. You're sitting at the Sumner Tunnel, and you're sitting at the toll system. And the guy in front pays the toll. The gate goes up, and boom. Okay, so this is sort of the automotive analogy of the problem we're trying to solve. If you work for Massport, what could you do to prevent everybody from gunning it? Now, let me just point out that this is not something we're encouraging you to do. Yes, officer, I learned this in lecture. It was a homework assignment. I had to try it out. Okay, so don't try this at home. What Massport should have built, okay, is an escapement mechanism. We're going to use 2 gates. Okay, one in front and one behind. And now, when you pay your toll, the front gate opens. That's fine. This car can go. After that car is gone, we can open a gate and let another one in to pay his toll. And when it's in front of the toll booth, we close the gate behind it, and so forth and so on. And you can see, using these sort of 2 strategies, okay, that these 2 gates, we come up with a strategy such that we never run the risk of having this sort of path that makes it all the way through the toll booth. That's exactly the analogy we want. We want a little digital toll booth as our memory element that never lets a cycle develop. There's none of this zoom, zoom, zoom. I hope I close the gate before my input changes because I don't want to reflect the latest. I want to sort of go in an orderly sequence and not just sort of zoom through, a bunch of configurations, all at once. Well, people get the idea of the escapement strategy, how this 2 gates actually solves the problem. The word escapement is actually the name for a particular little mechanical piece in your watch. So if you actually open up a mechanical watch, right, I don't know if anybody here owns a mechanical watch, but if you opened up one in the back, you discover that the gear that's actually connected to the spring itself has this little rocker bar that goes tick, 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 tick. And it's such that it has 2 teeth that are either catch the gear on one side or spin this way and let the gear advance 1 cog. And so the mechanism that translates the continuous energy of the spring to a bunch of sort of digital movements where the gear advances sort of jerkily 1 cog at a time, that's the escapement mechanism. And I've just described the toll booth analog of that mechanism. Okay, so send our last couple home for the evening. And the key is that there's at no time is there a path through both gates. We'll do that here. We're going to use back-to-back latches, okay, and we're going to jigger the gate signal here in such a way that there's never the time when both latches are open at the same time. Either the master latch is open and the slave latch is closed. Okay, that happens when G is 0. Or the master latch is closed and the slave latch is open. That happens when G is 1. Okay, if you're worried about the delay of this inverter, if you're saying, oh, but for a short amount of time, both G and G bar are 0 until the inverter changes or something like that, think about implementing this sort of negative edge, this negative latch, the latch that responds, with an opposite polarity of a gate. You could just wire up the mux a little differently and come up with something. No inverters need to be involved in this. I can design both a positive latch and a negative latch that doesn't have this pesky inverter delay. Okay, so when I say another word for the latch being open, the gate being open, is the latch is transparent. In other words, D is being reflected on the Q output after TPD. So when I talk about a transparent latch, that's a latch that's letting information through and is not in storage mode. Okay, so we have a no combinational path through the flip-flop. Okay, and we should notice that at any given time, either one of the latches is in transparent mode, the other one is in this positive feedback loop mode. So that means that somebody is always remembering something. So we're always in a situation where one of those positive feedback loops is busy remembering. And then we have this strategy for transferring information from the master to the slave, and that happens on the rising edge of the clock. On the rising edge of this clock signal, the slave latch opens. Information that has been waiting at the star node now finds its way to the output. Okay, so the only time the Q output changes, the only time when it will actually transition from 0 to 1 or 1 to 0, if it's destined to change at all, is right after the rising edge of the clock. Right when the slave latch opens is the only time the Q output changes. So this gives us the sense that the Q output is changing, is being triggered, the so-called register or flip-flop is being triggered by the rising edge of the clock. We've noticed the instant of time in which the clock rises, and that's when the Q output changes. Everybody sort of get that? So what we've done is we've built a digital escapement mechanism that cleverly allows information, new information to come into the latch. Okay, and at the rising edge of the flip-flop, what that does is it closes the master latch. It goes into memory mode, so it will remember the information that we're trying to store now in the register. And then at the rising edge here, that information that just started to be remembered by the master is now transmitted by the slave to the output. Yes, ma'am.
When you say it's closed, that's when it's in the loop and open?
So the gate being open and closed is the same thing as being in transparent. So when I say the latch is open, I mean it's transparent. It's letting information through. When I say the latch is closed, it's not letting information through. It's in memory mode. Okay. So if I looked at a timing diagram, so we're going to have a new schematic symbol here. So this was our symbol, the schematic symbol for latches. We'll not really be using any latches in the course. We're going to be using this magic thing called a D register, so-called because it has a D input. We're going to sort of come up with a schematic symbol that lets us know that it's an edge-triggered device. We know it's not actually triggered by the edge, but the Q output changes right after that edge by putting this little triangle here. So typically, if you see this sort of little pointy triangle right next to an input, it means that it's an edge-triggered input. It's that the device behaves as if it's the edge that matters, okay, on this particular input signal. You can see that in this diagram here, Q only changes when the clock, right after the clock changes. Okay, even though D is wiggling up and down and the middle node is wiggling up and down, the Q node will only change shortly after the rising clock edge. And you should look at this diagram to sort of see how, it's the value of D, okay, at the moment the clock goes high that becomes the next value of Q. So you can think of the register at the rising clock edge, it's sampling the D value, and that becomes the thing the register will now output for the rest of the cycle until we get another rising edge on the clock signal. And the clock signal is often periodic. And when you talk about a processor that has a gigahertz clock, we're talking about the frequency of these rising edges. So every billionth of a second or so for a gigahertz processor. Okay, there is one small technical detail. You should puzzle over this slide, and I'm going to ask the recitation instructors to actually make sure that you understand about this. We have to worry about the fact that the master latch is closing just as the slave latch is opening, and now we have sort of two things happening at once, and we have to make sure that that star signal, okay, doesn't change too quickly, because if it changed too quickly, it wouldn't meet the hold time of the slave latch. So we have to make sure that the contamination delay, how long this signal remains valid on the star, even though we're changing the G input. So we have to sort of make sure that we have a situation where this D signal meets the setup and hold times of the slave latch. And so as an engineer, if you ever have to design at the FET level, one of these registers, and I've had to do that, you have to spend a lot of time wondering if every possible power supply voltage and every possible operating temperature and at every possible, outcome from the manufacturing line, you know, fast P's and slow N's and slow N's and fast P's and fast and slow, and you know, all the different process corners and all the things that can happen that your register will in fact work correctly. And I can remember a very unfortunate circumstance in my past where I was very clever in my design and it almost worked everywhere, but there was one instance that it didn't work. Some combination of a particular process corner of fast P's and slow N's and a high temperature and a low power supply voltage, and the register didn't work quite as well. And that leads to customers calling up going, you know, in this hot room, this guy is flaky. You know, your computer isn't computing anymore. It doesn't seem to remember anything quite reliably. So this little piece of engineering is actually tricky business and involves a lot of analog simulation to figure out whether things are working correctly. So in general, we buy this. So when you call up TSMC and say, hi, I want to build a device, they give you a bunch of logic cells that they've designed that they guarantee to work in all the right conditions. And you say, your answer should be, yes, I'll use those, thank you. Don't try to design your own from the FET level. Okay, so let's talk about the timing that is related to this register. So remember, the register inside has both a master and a slave. After the rising edge of the clock, we have this sort of notion that the Q output will be changing, and associated with the change in Q is both a propagation delay and a contamination delay. And those are basically the propagation and contamination delays of the slave latch. Okay, because Q is connected to the slave latch, it's the output of the slave latch, and what we're doing is talking about the timing of changes of Q relative to the rising edge of the clock, which is really the only time the Q changes. So a register has those two timing specs, a contamination delay, okay, sometimes in the literature that you buy, it will actually call it the min TPD. That's not a very good name for it, but they're trying to tell you the contamination delay. And then the propagation delay of the latch, how long the so-called clock to Q time of the register. Okay. And then on the master latch front, because remember the rising edge of the clock is exactly when the master latch is going into memory mode. That's when we have to have a period of stability. So we have a setup and a hold time for the D signal in order for the master latch to work correctly. Right, we have to meet the setup and hold time for the master latch. And so we have these four timing specifications. A period of stability for D around the rising edge of the clock. Those are called the setup and the hold times respectively. And then a contamination and propagation delay of the Q output after the rising edge of the clock. Four numbers. And if you ever start doing digital design for Intel, these four numbers will be the things that keep you up at night and how to you'll earn your money. And why that's true, I'm going to show you in the next couple slides. Okay, but first let's talk about how we're going to use this in our circuitry. We're going to follow in 6004 a so-called single clock synchronous circuits. In other words, so this is our register symbol here. This is about as good as jokes get in 6004. And the idea is that we're not going to allow any cycles in the circuit. So there's no cycles here except right at the latch itself. In other words, we can have loops, but those loops are always broken by one of these registers. Right? And we know that these devices are all going to be triggered on a single signal. Okay, the so-called, so no combinational cycles. The cycles are all broken by these registers. We know there's cycles, positive feedback loops inside the registers, but we've been working very hard to engineer those so that they work correctly. Okay, we only care about the value of the register data of the inputs to the register here right at the rising clock edge, a T set up before the clock edge, right? So anything can happen in here so long everything is stable, T set up before the rising edge of the clock everywhere in the circuit. So at the time we're changing the state in the circuit, throughout the circuit, basically everything is quiet. It's been quiet for T setup. Right? So we're going to change our memories just when all the other electrical glitches associated with combinational logic, charging and discharging nodes has all died out, and everything's been quiet for a while. So, before the rising edge, someone says, "Quiet, class!" And everybody sits there very silently, and then I say, "Change the state," the rising edge of the clock, and now, all whatever breaks loose as that new signal propagates through the circuit and the combinational logic computes the values for the next state. Okay, so this is actually a very reliable discipline, And in fact, by choosing the clock period, we can make sure that period of quietness is enough to make everything work well. And I'm going to show you that constraint on the next slide. Okay, so what we're trying to do is to adjust our memories sort of at the quietest moment of time. Circuits that have multiple clocks start having issues with, the fact that you're changing over here, which might produce some noise just when I'm hoping to update my memory, and that noise might corrupt the value I'm saving. So multiple clocks are actually engineering challenges that you probably have to be careful about. So we have the second. I'm going to show you now how to use an actual piece of this synchronous circuit. I'm not going to show it to you today, but next lecture, you'll see it in recitation, and next lecture I'll pick up the talk here, where I'm going to show you the two basic timing constraints for how to design with registers in combinational logic. So that'll be for next time. Okay. Thank you all. We'll see you in section, and then good luck on your lab.